Welcome, everyone. Let's just jump right in because today we have an incredibly focused explainer lined up for you. We are looking at a highly specific and honestly potentially catastrophic fault in high-voltage automotive battery systems. It's known as P0B24. Now, I want you to think of this fault not just as some random error code that pops up on a screen, but as a severe electrochemical illness, one that strikes at the very heart of an EV's power source. Our goal today? We're going to diagnose this illness completely. We'll start with the microscopic symptoms that trigger it and go all the way up to the massive, factory-level engineering that's required to cure it. To make sure we cover everything, this explainer is broken down into 5 parts. We've got the root cause analysis, the BMS tech architecture and fail-safes, DFMEA design measures, PFMEA process controls, and finally, DVP&R validation. Okay, let's kick things off with Section 1. P0B24 root cause analysis. We're going to zoom way in, right into the microscopic world inside the battery cell itself. First, let's actually define the disease here. P0B24 isn't your standard run-of-the-mill battery drain. It's a highly dynamic physical and electrochemical failure. If you are a diagnostics engineer staring at the data logs while the car is out driving, you wouldn't see a nice, smooth power curve. No way. You would see severe, completely non-physical voltage fluctuations, high-frequency spikes, or these really irregular, sudden drops, specifically when the battery is under a dynamic load. Honestly, it looks completely erratic, almost like a sensor is just broken. But as we'll see, it's often a very real and very dangerous physical issue inside the cell. So what's actually causing this? There are 4 primary triggers for these erratic readings. First up, micro cracks. You see, high-frequency vibrations from the road and thermal expansion literally tear at the microscopic laser welds connecting the battery tabs to the busbars. As the car hits bumps, these tiny cracks open and close, causing massive spikes in electrical resistance. Second, we have separator microshorts. This is where microscopic metal dust from the manufacturing process or lithium dendrites from cold fast charging physically puncture the cell's separator, creating a tiny short circuit. Third, the active material or current collectors can physically detach inside the cell, causing extreme polarization distortion and resistance spikes when you step on the accelerator. And finally, trigger number 4 is external. It's high-frequency electromagnetic interference, or EMI noise, blasting from the motor's inverter, which completely corrupts the sensor readings. Right, so with all those threats lurking, how does the car actually survive? Let's move on to Section 2, BMS tech architecture and failsafe. You can think of the battery management system, the BMS, as a highly advanced immune system that follows a strict, real-time diagnostic roadmap. Step 1. The analog front end, or AFE chip, uses high-frequency differential sampling to constantly monitor the cell. But, that raw data is super noisy. So in Step 2, it passes through a second-order RC digital low-pass filter to clean it up. Step 3 is where the software monitors the dynamic slope. That's the rate of voltage change over time, or dV/dt. Based on that slope, the computer makes a split-second decision in Step 4. It either limits the state of power to protect the battery, or it throws a diagnostic trouble code. Now, the absolutely crucial part here is how the software tells the difference between a real power drain and a fake glitch. It uses what's called an equivalent circuit model, or ECM. The BMS algorithm compares real-time voltage against this model. A real electrochemical discharge, well, that has a relatively smooth slope that matches the ECM. But a loose wire, a microcrack, or an EMI attack, that creates a sharp, violent spike with an extreme dV/dt rate. It's kind of like using noise-canceling headphones. The algorithm specifically identifies and filters out that static to zero in on the real threat. But what if you just hit a really bad pothole? To prevent false alarms, the system relies on highly specific thresholds. To trigger a confirmed P0B24 code, that dynamic voltage drop difference between cells must hit 400 millivolts or greater, while the vehicle is pulling a heavy current of 100 amps or more. And here is the kicker. It must last for a debounce window of 500 milliseconds to 2 seconds. That debounce period is essentially the car's computer taking a deep breath, filtering out that random bump in the road, and confirming, yes, this is a sustained, real failure. The moment that threat is confirmed, the vehicle immediately enters survival mode, what engineers lovingly call limp home. From the driver's seat, a few things happen instantly. Regenerative braking is entirely disabled to prevent any wild power surges. The maximum discharge power is slashed by a massive 60% to keep that damaged cell from dropping below safe voltage limits. The dreaded yellow turtle light and malfunction indicator lamp light up on your dash. And finally, Pure EV mode is disabled. The car forces itself to rely on the hybrid engine just to get you home safely without causing a catastrophic battery failure. So the car caught the failure, great, but just diagnosing it isn't enough. We need to engineer this failure out of existence entirely. Welcome to Section 3, DFMEA Design Measures. This is the phase where engineers essentially alter the physical genetics of the battery. Look at this number right here, 8. In the intense world of automotive safety, a severity score of 8 in a DFMEA analysis is massive. It literally means the risk of a sudden, unexpected loss of power while driving is so incredibly high that the engineering countermeasures have to be absolutely bulletproof. To combat a severity 8 risk, engineers deploy some truly brilliant physical defenses. Remember those microcracks we talked about? To stop those, they use S-shaped or wave-shaped flex cables for the voltage sampling lines. That simple S-shape acts as a physical shock absorber, completely absorbing thermal expansion and road vibrations before they can shear the weld right off. Next, they armor the battery cell internally by coating the separator with high-strength aluminum oxide ceramic. This physically blocks those lithium dendrites from puncturing the cell. And to top it off, they bake second-order RC low-pass filters directly into the hardware circuits to just kill high-frequency EMI noise before it even has a chance to reach the processor. Moving right along to Section 4, PFMEA, Process Control. Because let's be real, you can have the greatest design in the world, but if the factory builds it wrong, you still fail. The factory floor requires a rigid, zero-tolerance environment. Take laser welding, for example. The process has strictly locked key control characteristics. That means the spot size, laser power, gas flow, and speed absolutely cannot deviate. To prevent those microscopic metal shavings from causing internal shorts, the entire assembly must happen in an ISO Class 6 cleanroom with constant negative pressure. And at the end of line, or EOL, the contact resistance of those welds must measure under a microscopic 0.05 milliohms. Plus, every single unit goes through a high-frequency pulse discharge test to forcefully expose any weak connections before it's allowed to leave the plant. To actually achieve this level of precision, the modern assembly line uses some total sci-fi level tech. Have you ever heard of online coherence tomography, or OCT? It's exactly what it sounds like, a 3D, non-destructive, real-time scan of every single laser weld. It monitors the precise depth of the weld pool instantly, guaranteeing that no hidden air bubbles or weak joints escape production. It's incredibly thorough. Finally, we arrive at Section 5, DVP&R validation. You can consider this the clinical trials phase. Before mass production is ever approved, engineers must subject all these design and manufacturing defenses to absolute, unforgiving torture. Just take a look at the physical abuse required here. The battery components, including those fancy S-shaped cables, are placed in a thermal shock chamber. They swing violently from -40 degrees all the way to 85 degrees Celsius in under 10 seconds. And while that's happening, they are hammered with 3D random vibrations for 300 straight hours, strictly following ISO standards. The pass criteria? After all that torture, the microscopic contact resistance must remain completely stable, staying under 0.05 milliohms. 0 cracks allowed, 0 failures. Then, if they survive that, comes the software torture test. Engineers intentionally attack the system. They inject a vicious 10 to 20 kilohertz electromagnetic noise spike, simulating the absolute worst-case scenario coming off the vehicle's motor. The hardware RC filter is required to crush that noise by at least 40 decibels right off the bat. Simultaneously, the software must instantly identify the impossible voltage jump, anything greater than 0.5 volts in 10 milliseconds, label it as invalid noise, and just ignore it. And through all this crazy interference, the battery's state of charge calculation cannot drift by more than 1.5%. The absolute final exam for the BMS brain is the current voltage correlation test. Engineers simulate 2 different scenarios here. In scenario A, they drop the voltage exactly when the vehicle asks for high current. The system must recognize this as a real physical fault and slash power by 60% within that strict 15-second debounce window we talked about. But in scenario B, they inject a random voltage jump while the current is setting at 0 amps. The software must be smart enough to know that's physically impossible. It has to recognize it as sensor static, log a background code, and crucially, do not cut power to the driver. So the big takeaway here is that when validation is finally finished, the factory is locked in with these strict metrics. 100% of welding parameters must stay within the control bounds. The automated systems must intercept every single piece with a resistance equal to or greater than 0.05 milliohms, and the overall process capability index, or CPK, must be 1.67 or higher. That number represents an incredibly high standard of manufacturing consistency. It guarantees that every single battery rolling off the line is immune to P0B24. Which brings us nicely to our conclusion. We've dissected this highly dynamic fault all the way from a microscopic crack to a system-wide failsafe. But it leaves us with a pretty compelling question. To truly master our understanding of high-voltage battery defenses, shouldn't we take this local dynamic resistance fault of P0B24 and compare it directly to a full-pack resistance growth failure like P0AC4? Understanding the difference between a sudden localized spike and a total pack degradation might just be the next absolutely crucial piece of the puzzle. Thank you so much for joining me on this explainer, and keep learning.